Good morning, everybody. Welcome to sunny but cold Monday morning, a Chem 11:05 with your host, me, Dr. White. Hi. All right, important announcement. Due to some personal commitment, uh, I will be starting only today my office hour from 6 o'clock, starting at 6, and I'll go till 7:15. Again, and I sent out an email to all of you. My office hour tonight only will be from 6 to 7:15. I have an appointment I have to go to, and I probably won't be home till about 5:15, 5:30-ish, who knows, somewhere around that. This way, I'll be on time, so if you need help. Also, hand in labs. Last week, I made a mistake. The lab that was due last Tuesday, I had on Wednesday, it shut off from Blackboard. I since changed that. You've got time to hand it in today or tomorrow. Hand it in. It's 10 points. So don't miss out on it. Also, if you're having problems, and a lot of you, at least as of Saturday, hadn't handed in the gas lab, lab. If you're having problems with it, come to my office hour or ask me tomorrow after lab. All right, important announcement besides what I just said. We have finished all the material for test 3. On Friday, I will go through the chapter 5, part 2 problem set solutions. So if you haven't worked on them, work on them. That way you'll do good on test number 3. So it's time for a new chapter. Oh, I can use this. New chapter time. I got to get a wider lens webcam so you can see when I do this. Nah, I won't. But anyways, new chapter. This will be on test 4, not test 3. But let's get going. How many of you have ever heard that there's an acid in your stomach? Give me a thumbs up if you've heard that. I see a couple of people. Or you might have heard your stomach fluids are acidic. You might have heard that too. Or the liquid in your battery for a car or your friend's car or parent's car is called battery acid. What's the word acid? Well, this chapter is probably one of the most, if not the most useful chapter for you personally the rest of your life. And what is it? It deals with acids and bases. Now, one of the most difficult challenges in chemistry was to define what is an acid, what is a base. It wasn't that simple. In fact, it was only until about 100 years ago that they actually found a way to do this. Now, originally, a chemist named Arrhenius came up with an acid-base theory. Now, watch closely. Click this slide. I'm turning the switch. It won't be on the test because you'll see later there's another theory we now use. Now, the Arrhenius theory, an acid, an Arrhenius acid, is a hydrogen-containing compound that, and this is important, in water produces hydrogen ions called H+. And an Arrhenius base is a hydroxide-containing compound that in water produces hydroxide ions. Hydroxide is OH minus, hydrogen ions H+. Now, I'll give you some examples later. Now, switch is on. When we talk about acids, They're important acids you should know the name and structure of. I even wrote out the whole word. All right, let's talk about some important acids in our daily life. The first one is hydrochloric acid. And the structure of hydrochloric acid is HCl. Oh, I forgot some of you don't know. It looks the same to me, but anyways, HCl, hydrochloric acid. And this is the acid in your stomach. Now, I always think of it as a great miracle of life that both you and I have cells in our stomach that make this compound, hydrochloric acid. Now, another one that you should know, this chemical structure and the name is sulfuric acid, and that's H2SO4. This is sulfuric acid. That's hydrochloric. And sulfuric acid is a very important acid. It's probably the most widely produced chemical in the United States, if not the world. Yes, H2SO4, because it's used for many things. Now, one of the things it's used for is your battery acid in your car. It's also used to help make other chemicals. Now, another important acid is nitric acid. Now, there we have nitric acid. And a combination of nitric and sulfuric is used for many things. One of them is to make explosives. The other thing is nitric acid allows you to make certain chemicals that are made into other chemicals, such as the dyes for your clothing. Now, the last one, I will not ask you to learn the structure, and I'm going to use organic method of writing it, not the empirical formula, and that's acetic acid. Again, this is a carbon with 3 hydrogens attached to a carbon with 2 oxygens, and one of the oxygen has the hydrogen. Now, why would I ask you to learn about acetic acid? Well, guess what? Spence killing you? I hope not. You all have acetic acid in your house. And now all of you are probably, no, I don't have acetic acid in my house or apartment or condo. I would know if I had acetic acid. Well, you do, lots of it, I'll bet. Oh, by the way, if I ever say I bet, I already know I won. So never bet with me. Never bet with me. Where do you find acetic acid? Well, if you take about 4% acetic acid and about 96% water, mix them together, you get a homogeneous solution, which we have a name for. Vinegar. Vinegar is a mixture of water and acetic acid. Whatever type of vinegar you have, it's essentially acetic acid and water. Now, different types of vinegar have minor other things in there that give it its taste. If you've ever had apple cider vinegar, it tastes different from what they call white vinegar. No, it's not named after me. I'd like it to be, but it's not. And that's the standard, just acetic acid and water. So you can have apple cider vinegar, you can have champagne vinegar, you can have wine vinegar, and you can also have rice wine vinegar. And that's one of my favorites. This isn't it. Hold on. And the best brand out there, which they have here, is, and I probably pronounce it wrong, Marucan. And their basic gold label like this rice wine vinegar is really good. Don't buy it from Amazon. They're ripping you off. You can buy it just about any supermarket nowadays. I know my local one sells it. And I bet you could even get it at Walmart. Hold on, let's find out. Oh, I might have lost that bet. Hold on. Yeah, they may not have it. But anyways, acetic acid is with water is a mixture we call vinegar. And it's an acid. And all these, when you put them in water, give up a proton. If I have this in water, this dissociates in water. And this tells you in water that's an Arrhenius acid. Now, there are also bases you should know. Now, probably the most common base is sodium hydroxide, which has the chemical formula you should know called NaOH, which you've heard me use. Now, it had the old ancient name, which is still being used, called lye. How many of you have ever heard of lye soap? No one? No one's heard of lye soap? Wow. I'll teach you more about it later in the semester. But lye soap is made with sodium hydroxide, and that's how it got the name lye. Now, another base is potassium hydroxide, KOH. And this was originally discovered in the ashes from the fire underneath the pot or in your fireplace. And therefore, it was found in the ashes underneath pots, cooking pots, and they get the old name is potash, and that's potassium hydroxide. Now, a very important base is ammonia. Ammonia is NH3. Now, ammonia at room temperature, this abbreviation is a gas. Under high pressure, you can, under the right container, you can make it into a liquid. But as soon as it comes to room temperature, it becomes a gas. Now, one of my more, how should I say this, unpleasant, but still chemical memory was I was at one plant where we used a lot of ammonia, and because someone was sick and I was there supervising, helping out, I had to get in one of those hazmat suits, you know, with the gloves and everything, the hood and everything, air tank on your back, mask for breathing. That covered your whole gas mask. And it was 90 out, high humidity, and I had to supervise unloading a railroad car of liquid ammonia. Because if I took the mask off, I'd probably be dead now. Good news, I didn't. But it was not fun because you've got this gas mask to whole hazmat suit on. It's 90 and humid. You feel like you're in a rubber suit. All of a sudden you start sweating. It's going like this. And you can't take the mask, go like that because you'll be dead. And you go like this to try and get it away from your eyes. Not a pleasant time, but important. Now, there's one last space I'd like you to talk about. That's sodium bicarbonate. And you all have this in your kitchen, or a lot of you do, and that's baking powder. And sodium bicarbonate, you should know, has the formula NaHCO3. And this is called sodium bicarbonate. And it also is a base. Now, a base is something that produces hydroxide ions in water. If we look at sodium hydroxide, which is a solid at room temperature, and if we put it into water, it will form these ions. And this is the hydroxide. It's not the governor of the state of Illinois, so I'm going to ignore it. A couple more. Oh, they gave up. All right. So again, hydronium ions, hydroxide ions, when they're formed, is indication under Arrhenius theory of acids and bases. So these are acids because they form a proton. This is also known as a proton. Because what's something with no neutrons, no electrons, one proton? A proton. But it's also called the hydrogen ion. It turns out both of these are very important in our body and in the world. Oh, by the way, next time you happen to be near a refrigerator or in a supermarket, pick up a bottle of ketchup. It has acetic acid in it. Why? Because it's made with vinegar. Same thing with mustard. Mustard has vinegar in it, therefore it has acetic acid in there. And finally, pick up a jar if you don't have some in your house, either relish, the green kind we sell in Chicago that glows in the dark, or pickles. And that also has acetic acid in them because relish and pickles also contain lots of vinegar. Now, there was a serious problem with the Arrhenius theory. And the most glaring part is it only works when you're in water. What if you're not in water? A lot of chemistry happens not in water. Well, guess what? It fails. And that's why I told you don't turn the switch off. What's an Arrhenius acid or base? Turns out about early 1900s, two independent chemists came up with the same theory at about the same time that solved the problem, what's an acid and base? Part of the problem of solving that problem is if you come out with a new theory, this is an acid, this is a base, all the Arrhenius acids and bases have to be acids and bases under your theory. And this new theory did. And if I had a dial, I just turned it up to 5,000 if it only goes up to 10. This is important. All right, the Arrhenius theory does not explain acids and bases in non-aqueous, non means without aqueous water solutions. So what happened? Well, two chemists, Bronsted and Lowry, came up with a theory, And we now call that the Bronsted-Lowry theories of acids and bases. Whenever I'd put a couple stars and then put IMP in the left margin of my notes when I was an undergrad student in grad school too, that meant I better know this stuff. So what's a Bronsted-Lowry acid? It's any substance that can donate a proton, H plus, to another substance. And the best way that I like to think of it is a Bronsted-Lowry acid is a proton donor, proton being H plus. So something can give up a proton, it's an acid, Bronsted-Lowry acid. We generally drop the term Bronsted-Lowry because that's the key theory now used today. So I've got my proton here, take it, take it. And if I give it to you, I donate it to you, I'm an acid. So an acid, Bronsted-Lowry acid, is a proton donor. Proton donor. Here, take my proton. And I would be an acid. And if we look at HCl, it will give up a proton. And when it does, it gives up H plus, Cl minus is left behind. So this is an acid because it will give to other things a proton. Now, what's a Bronsted-Lowry base? Good question, thank you. But before I do that, it's time for me to be subtle. Well, I'm giving away all the secrets of my past, how to take good notes, make sure you get good scores on a test. But anyways, know this. What's a Bronsted-Lowry base? And that's any substance that can accept a proton from another substance. And this is called a proton acceptor. And turns out sodium hydroxide, when you react it with water, takes a proton and if I were to be able to label this oxygen right here, it would be this oxygen right here. So if you're a Bronsted-Lowry base, you accept protons. Remember, proton is H plus, and that's a base. Let's go through this again. This is probably one of the most important concepts in all chemistry that I'll teach you this semester. What's an acid? Proton donor, H plus donor. What's a base? A Bronsted-Lowry base, proton acceptor. So if I'm a Bronsted-Lowry base, I'm saying, come on, give me your proton. Come on, give it to me. Give me your proton, I accept it. If I'm an acid, here, take my proton. And if we were in front of the class, I would have done the same thing. Now, something very important. Water, which is an amazing chemical, you don't think of it as, but it is, will react with a proton to form the hydronium ion. So if I have an acid and water, an acid is a proton donor. It will immediately react with water to form the hydronium ion H3O plus. And this is a covalent bond to oxygen. It's a plus charge because oxygen donates one of its electrons to the shared pair of electrons in the hydronium ion. And you should know hydronium is H3O plus. Now, one of the things that I mentioned earlier was in Bronsted-Lowry acid-base theory, you don't have to be in water. If we look here, this is a H plus Cl minus. This donates the H plus to the ammonia and H3 to form the ammonium anion or cation. Plus the chloride anion. So HCl, hydrochloric acid, is an acid. Why? Because it donated a proton to ammonia. Now, ammonia, as I mentioned earlier, is a base, Bronsted-Lowry base. And why is this true? Because it accepted a proton. So when you're looking at an acid or base under Bronsted-Lowry theory, which we all do, you follow the proton, H plus. And here it went from HCl, hydrochloric acid, to ammonia when you mix them together. Now, this is an interesting reaction. How is it interesting? I'll have to find a YouTube. If I have a beaker of ammonia in water, which is really I'll talk about it later, and a beaker of HCl, there's some vapor, you learned about vapor in solutions, of ammonia and hydrochloric acid. When they come together, they form NH4Cl. When not in water, in the gas, it's a white solid. And when you do that, it looks like smoke. And you put the two together, and all of a sudden you see smoke generated. It's really ammonium chloride. Hold on, let's see something. All right. Let's have some fun with chemistry.
Hello guys, this is another episode of the Backyard Scientist, and today I'm going to show you the reaction between hydrochloric acid and ammonia. And there's a reaction in the gas phase and the liquid phase. And you can see that even though that I have the hydrochloric acid with a cap on it, it's still reacting with ambient ammonia in the air. So what happens when I take this off is the hydrochloric acid vapors immediately react with the ammonia in the air, and it produces a very strong smoking effect. I always enjoy it.
Is chemistry cool or is chemistry cool? It's cool. Now you know I'm a chemist because I'm happy. And that's a way of generating what looks like smoke. And there's a story I can't tell you about what some high schools did, That scared people and thinking, oh, this locker is on fire. Junior chemists can be dangerous too. Anyways, what you saw in that video was the vapors of hydrochloric acid were reacting with ammonia by transferring a proton to ammonia. And if you're not in water, which you can write this salt, and it is a salt because, and this is a white solid. And that's what you saw in the air, was this being formed in a very dilute amount in the air. And that's what the white, it looked like smoke, but it really wasn't smoke. Now, when we talk about acids and bases, first of all, I've got to teach you something that's not in the book. Otherwise, this won't make any sense. Oh, guess what I forgot to do, or I can't find? Nope, I forgot to do it. Hold on. All right. There's something called an equilibrium. And an equilibrium, this won't be on a test, is when you have two opposing reactions. And let's look at this. A plus B reacts to make C plus D. Now, if I were to react C and D, and if it was an equilibrium, C and D reacts to make A and B. And we use this double-headed arrow. Sometimes my software will draw it this way. A lot of times I'll draw it this way, or sometimes this way. And this double-headed arrow tells you you have an equilibrium. Now, there's something, again, I don't teach in this class, I teach in 1211, that's called the rate of reaction, how fast something goes to make products. And equilibrium, the forward and the reverse rate of reaction are the same. So let's go through this again. A plus B makes C plus D. Now, if I were to take C and D and react them together, I would get A and B. So when this happens, both the reactions going this way and this way happen at the same time. And the rate, how fast they go one direction or the other, are the same. And unfortunately, we don't teach it in this class, but there's a whole area of chemistry dealing with equilibrium and examples of where equilibrium play an important role in our life, your lungs, and I think either your kidneys or liver, I always forget which one of those, are dependent on equilibrium. Also, another thing, not to scare you, even though it was Halloween yesterday, your blood is dependent on equilibrium. Yep, your blood. And that's something that keeps you alive. And that's not what I want. So when we have an acid-base reaction, there's an equilibrium. And proton transfer does not happen for most acids 100%. There's an equilibrium here. Now, HA is the general way chemists call something an acid. B, guess what? That's a general way of saying a base. Now, if this is an acid and this is a base, when it goes to the right, the acid donates a proton, H plus, to the base. And notice we have B plus H plus. Now, when this loses H plus, this becomes A minus. And this is what we call a typical acid-base reaction. Acid donating a proton to a base. Now, if you take this and this, if you could have separate, it goes back this way. There's something called the equilibrium constant, depending which side has more, which I'm not going to get into. But the important thing here is something called conjugate acid-base pair. And these are two species chemicals that differ by only one proton. Now, if I come back here, and let me redraw it. By the way, switch is on. You should know this. If we look at this, we have HA is our acid. How do we know it's an acid? Well, let's look at its conjugate. A conjugate is something that differs by H plus. So when we go in this direction, HA is an acid and its conjugate is A minus. This is the conjugate of HA. Now, if we look at B, on this side, we have HB plus. And again, it only differs by H plus. And this would be the conjugate of B. Now, when you go in this direction, you look at the conjugates. And the conjugate, what you make on the right, or in the direction you're going, you say, has it lost a proton, H plus, or gained it? And one of the things I will tell you, a lot of students go, oh, this is hurting my brain. I don't know about that badly, but they have a lot of trouble following H plus. So my advice to you is just follow a hydrogen, H. Forget about the plus. It will give you the same results if it's an acid or a base. And you have to also be able to identify the conjugates. Now, if we look at compound HA, and I'm going to call that X and B is Y, A is Z, HB plus is W, X is an acid. This right here. How do we know? Because to going to its conjugate Z, it loses a proton. Now, Y going to its conjugate W accepts a proton. Remember, an acid is a proton acceptor. I got that wrong again. Once in a while, I have a bad day. And today is that day. Dr. White has certain things on my mind that I should have cleaned out. Acid is a proton donor, and a base is a proton acceptor. And B going to W accepts a proton, and therefore it's a base. Now, in chemistry, we have a concept called conjugate acid, conjugate base. And by definition, when you have an equilibrium, acid-base equilibrium, the chemicals on the right are defined as the conjugate. Now, what is Z? Is Z a conjugate acid or conjugate base? And if we look at this, how do we find out? We say if we go from A minus to HA, does it gain or lose a proton or accept a proton? In this case, we have A minus, follow the star, none. We have HA, so going from Z to X, A minus has accepted a proton. Proton acceptor is a base. If it's on the right side, it's conjugate. So Z is called a conjugate base. And let's look at W, HB plus. When it goes from HB plus to its conjugate Y going this way, is it an acid or base? Well, let's look. Follow the hydrogen. Has 1 here, has 0 here. So that means it's donated, given up a proton. And something that gives up a proton is an acid. And because it's on the right, it's a conjugate acid. Same thing here. So this is an important skill in acids and bases. What's the acid? What's the base? And in equilibrium, what's its conjugate acid and base? And if we look at the following, and if we see sometime near future, name the acid, base, conjugate acid, and conjugate base for this equation. And the first thing you have to do is identify conjugates. And what are conjugates? Species that differ by only 1 proton or hydrogen. That would be easier. This has a chlorine, this has a chlorine. The only difference is this has a hydrogen, this doesn't, plus the charge. So X and Z are conjugates. Now, if we look at NH3Y, and we have, this has the nitrogen. The only thing here that has the nitrogen is W, NH4 plus. And notice this has 3 hydrogens. This has 4, it has a plus side too, but discount hydrogens. This is a conjugate. It differs by only 1 proton, H plus, but for this class, it's easy, follow the hydrogen. Now, if we look at going from X to Z, this direction, does HCl accept or donate a proton? Let's see if I can get it right now. Sorry about rating. Remember, a proton, we're talking about H plus. So going from X to Z, HCl loses a proton, donates it, so it's an acid. Now, if we look at ammonia, NH3, going from Y to its conjugate W, does it gain, accept, or lose protons? 3 hydrogens, 4. It accepts, so it's a base. Now, by definition, everything on the right are conjugates, so I wrote that in. Now, if we look at going now this direction, going from Z to X, is conjugate. Does it gain or lose a proton? No protons or hydrogens, 1 hydrogen, actually proton. So something that accepts a proton is a base. And therefore Z is called the conjugate base. And finally, W going to Y, it's conjugate. Again, going now this direction, NH4 plus, NH3, count just the hydrogens, it's easier for you. 4 to 3, does it lose or donate a proton or accept or gain? It loses it. What's something that loses or donates a proton? It's an acid. And that's a conjugate acid. So this is an important skill. We'll practice this more, but I wanted to go through this. Now, first time you see that, you say, oh, what's going on here? Yeah, it's a little confusing. When I was an undergrad first time, I was a little confused, but I'll practice it with you. Now, if I look at the clock, we're just about out of time. Remember, my office hour tonight will be starting at 6, not 5, and go till 7:15. If you haven't handed in the gas law lab, come to my office hour so I can help you so you can hand it in. It's already late, but you can still get a lot of points. And don't forget, the molarity lab we did last week is due tomorrow. So make sure you do your labs. And with that, I'm done. Gang gesund, be healthy. I'll see you tomorrow. Bye.